Good morning. I welcome you all to this session of fluid mechanics. The last class we were discussing about the moving pressure wave in a fluid for the water hammer problem when the valve is suddenly stopped, and we were on the way to deduce the expression for pressure rise due to the fluid deceleration to rest and the expression for the velocity of the pressure wave. So, if you recall it, we see that we deduce this expression for the pressure rise in the water which or liquid for its coming to rest is this much delta P by rho g, it is the pressure head, rise in pressure head, and we deduced up to this that delta P by rho c square is delta P by E plus delta A by A, if you recall the earlier deductions. Then from here we can write c square becomes equal to delta P by rho, or that we can write delta P by rho into delta P by E plus delta A by A, all right. And this can be written as delta P, if I take delta P by E as common, this can be written as E by rho into 1 plus E by delta P into delta A by A. So, this is E by delta P delta A by A. Now, here I like to replace delta A by A from such consideration. What is delta A by A? If we consider a circular pipe where A is proportional to the square of the diameter, delta A by A can be written as delta D, that is change in its diameter, delta D. So, delta D by D in terms of the circumferential stress, if we consider this pressure rise in the fluid causes a circumferential stress, and if E is the EP is the modulus of elasticity for the pipe material, so this can be written as 2 sigma T by EP. So, therefore, delta A by A is, so delta T by 2 delta D by D is 2 sigma T by EP. So, therefore, if we now just substitute this 2 sigma T by EP, now before that I want to write that sigma T, the circumferential stress, can be also expressed as in terms of diameter P d by 2T. This is also comes from the consideration of the strength of material. That means the circumferential stress is related to the internal pressure which causes the circumferential stress, diameter 2T, where T is the thickness of the pipe, thickness of the pipe. Now, if we substitute this sigma T there, then what we get? We get delta A by A is equal to, if you substitute this sigma T as P d by 2T, so P d by EP into T. Now, if this delta A by A is substituted in this expression of c square is equal to E by rho 1 plus E by delta P delta A by A, we finally get an expression C is equal to, you get an expression E by rho divided by 1 plus E d by EPT. E is the modulus of elasticity for the liquid and EP is the modulus of elasticity for the pipe. D is the diameter of the pipe considering circular in cross section. T is the thickness of the pipe. So, these whole to the power half. Now, in all practical cases we see that D is greater than T. There is no doubt diameter of the pipe will be greater than its thickness, but EP is much greater than E. It is by order of magnitudes, 2 order of magnitudes more, that is the modulus of bulk elasticity or the modulus of elasticity for the pipe material is 2 orders more than that of the liquid. So, therefore, ED by EPT is usually much less than 1. So, we can neglect it. So, that C comes equal to E by rho. For all practical purposes, E by rho to the power half. This is the expression for the wave velocity. C is equal to E by rho to the power half. So, we can give an example. What is the error of neglecting this? That if you consider water whose E at 20 degrees Celsius is equal to 2.2 into 10 to the power 6 kilonewton per meter square and rho is 1000 kg per meter cube, if you take this value and calculate C from this, you get C is equal to 1482 meter per second. Now, if we consider the pipe material, then you will have to take for a particular pipe, if you consider steel as the pipe material, then EP for steel is same to into 10 to the power 8 kilonewton per meter square. So if you take some typical values of D and T as some value D is 75 millimeter for example, and T is equal to 4 or 6, whatever you take 6 millimeter, you get this value of C as 1390 meter per second if you consider by this formula considering ED by EPT. So therefore the difference is almost 6%. So we can neglect this. So for all practical purposes C is taken as E by rho whole to the power half. So this is the expression of the wave velocity. So we get the wave velocity expression as C is equal to E by rho whole to the power half, and changes in pressure rate delta P by rho G is C V0 by G. So these two expressions are very important from analytical point of view. Now we will come to a very interesting phenomenon. Now that is, when this pressure wave is generated in a column of fluid by suddenly decelerating the fluid, for example stopping the valve. There is a pipe, there is a flow is coming from a reservoir and the valve at one end is stopped. So that at the downstream location flow is decelerated to 0 and gradually the liquid column comes to rest and pressure is increased by the propagation of a pressure wave from downstream to upstream. So what happens, because of the finite length of the tube, so this propagated pressure wave goes to upstream the reservoir end and again comes back as a reflected wave to the downstream end of the valve, and again as a reflected wave from the valve end it goes back. So there is a repeated to and fro movement of the pressure wave which creates the problem, the pressure fluctuations and the knocking to the pipeline. So this situation of pressure fluctuation is well depicted. How it is well depicted we see now. Let us see the situation, the reflection of waves and pressure fluctuation. Let us consider an inviscid fluid. Okay, so this is the reservoir. Let the head H0 is maintained fixed, that is the initial head on the reservoir. When the pipe valve is closed, this is the initial. Now valve is open, so then what happens? So initially the valve is not closed, the other valve is open. So we start the problem from the opening of the valve. It is under a steady flow velocity V0 and this under a head H0 constant. So at t is equal to 0, this is the situation depicted, that this is the H0 head, constant head at which the liquid is flowing at a constant velocity or a steady state velocity V0 when the valve is wide open. Now the instant when the valve is closed, so a pressure wave is generated at the downstream end, that is the valve end, and it is moving with a velocity c relative to the fluid we know. So we see at any instant 0, t is equal to 0, rather within t is equal to 0 to t is equal to L by C. Now one thing you have to know, that when the velocity of propagation is c with relative to the fluid, so therefore the pressure wave takes time to reach the reservoir end, a time L by C. So during that time between 0 to L by C, the pressure wave will move to some intermediate portion of the pipe. So this is the situation where this portion, the downstream portion, the pressure has increased to a value delta H whose magnitude is CV0 by G, which we have already deduced. And this upstream part of the liquid is moving still with the velocity V0 and its head is H0, the initial head, where this head is more than the initial head by this amount delta H. This is the positive sign, this is the negative sign. So at t is equal to L by C, what will be the situation? Situation is like that. At t is equal to L by C, the entire fluid in this pipeline is at 0 velocity and the head or the pressure in this pipeline is increased from the initial head H0 by an amount H0 plus delta H. But this situation is an unstable situation. Why? You see, the liquid in the pipe or reservoir is under a head H0, that is initial head, whereas the liquid in the pipe which is at rest but at a higher head than H0, H0 plus delta H. So this causes the flow of the liquid to the reservoir, that means liquid will rushes into the reservoir so that the pressure in the liquid is equalized to H0 pressure. So this process of rushing the liquid at high pressure in the column to the reservoir to equalize the pressure again to the H0 is conceived by movement of another pressure wave which is conceived as a reflected pressure wave from the reservoir end to the downstream side, that means valve end. And the action of this pressure wave going from the reservoir end to the valve end is to superimpose a negative delta H, a negative pressure head minus delta H, the negative pressure head of delta H on this, so that ultimately the pressure head is coming to H0. So this is the situation between a time interval of L by C to 2L by C, because it is from the initial, again this pressure wave to reach there will take a time L by C. So at a time, after a time 2L by C only this reflected pressure wave will reach there. So that any time in between from L by C to 2L by C, this situation is like that. That is, the reflected negative pressure wave has reached here, which has superimposed this part of the fluid from where it has passed, that is the downstream, compared to this moving pressure wave is the head is H0. Whereas this part of the liquid is still at a higher head delta H and velocity is 0. That means when the pressure wave has passed the reflected pressure wave or negative pressure wave from the reservoir end to this valve stream end, so when it passes through the fluid, it sets a velocity V0 in this direction, because physically the fluid is rushing into the reservoir and its head is being restored to its original value H0. That means minus delta H pressure head is superimposed on the fluid by this moving pressure wave. So this is a situation between a time of L by C to 2L by C. So exactly at time t is equal to 2L by C, this pressure wave has reached here. This is the reflected pressure wave from the reservoir end, which is a negative pressure wave. When it has reached here, the entire fluid or liquid is at head H0, that is the initial head, but it is moving in this direction, V0, towards the reservoir. Okay, but this situation is again unstable. Why? When this V0, that means out of inertia, so this liquid is still moving in this reservoir with a velocity V0 when the entire fluid has reached a pressure H0. So to maintain that inertia, the liquid, that means with a velocity V0 in this direction, the liquid suffers a decompression. That means the pressure in the liquid column decreases. This is being conceived by again the movement of a pressure wave, negative pressure wave, from the valve end to the reservoir end. Means the action of this pressure wave is to superimpose again a negative pressure head, which is again the delta H, magnitude is same, C V0 by G on the fluid element. That means again a pressure wave will move after the time t to L by C in towards the reservoir end by superimposing a negative pressure head in the fluid, and again to make the fluid at rest. That means this V0 physically, this velocity in this direction will be arrested when there will be a negative pressure created in the liquid column in the pipe. So this is the situation for the time instant t between 2L by C to 3L by C, when the negative pressure wave has moved up to this point or this section from the valve end, where the velocity is set to 0 and the negative pressure rate of delta H is superimposed. This is the H0. This is the H0. Whereas in this part of the fluid, it is still moving with V0 velocity in this direction, that means in the reservoir direction, and the pressure wave is moving in this direction with a velocity C. So therefore we see at time t is equal to 3L by C, this pressure wave will again reach the reservoir end. So when this situation corresponds to a situation when the entire liquid in the column is at a negative pressure from the original pressure, uniform by delta H, negative pressure. That means the entire liquid column is at a negative pressure, whereas the reservoir fluid at H0 pressure. So again a fluid will come from the reservoir to this column. That means again a positive pressure wave then will travel from the reservoir end to the valve end after a time t is equal to 3L by C, whose action will be to superimpose a plus delta H pressure rate on the fluid column. So this is moving. So a time of t between 3L by C and 4L by C, we see the pressure wave is moving like that, and in that case the liquid is moving from the reservoir to the pipe. That means to set the fluid a velocity V0 in this direction, and again to counterweigh this minus delta H from H0, so that the fluid head is H0. Okay, and this part is again at delta H, and this is moving with C velocity. This part is delta H and V is equal to 0. That means this situation. So when this wave is at this position. So exactly at t is equal to 4L by C, then the entire liquid column will be at H0 head and with a velocity V0 in this direction, which is same as that at t is equal to 0. So at t is equal to 2L by C, the entire liquid is at H0, but its velocity is in the opposite direction to that of the initial direction. That means towards the reservoir. So only at t is equal to 4L by C, we get the initial condition or initial situation to be restored. That means the entire liquid in this column or in this pipe is at a head H0 and its velocity is V0 towards the valve. So therefore we see a cycle of events is completed whose time period t is equal to 4L by C. And this cycle of events will be repeated indefinitely if the fluid is inviscid with the amplitude remaining undiminished. Amplitude means this is the pressure head remaining undiminished. This cycle of events will be repeated indefinitely. However, in actual cases, because of the viscosity, the amplitude gets diminished and ultimately it is dying out after few cycles. Okay, this is the reflection of waves and pressure fluctuation. Now let us find out that due to this reflection of waves to and fro, what is the situation of pressure fluctuation or pressure versus time at some location in the pipe or at the valve end. Let us consider, so this is the valve. Let us consider that this is the H0. Let us consider what is the pressure fluctuation due to this thing at the valve end or at any location. Let us consider the point at the valve end, and if we try to find out what is the pressure fluctuation due to this movement of this pressure wave at the valve end, at any point at the valve end here. So at t is equal to 0, let this is the time. At t is equal to 0, immediately the pressure goes from H0, it is H0 to delta H, that means to delta H. So this is delta H, which is CV0. We know that delta H is CV0 by G. So this will move to a distance L with a velocity c. So it will come here and then go again here, which would take 2L by c times, during which the pressure head will remain as 2L by delta H. So up to a time of 2L by c, the pressure head here will remain as H0 plus delta H. H0 is the initial head. Then at 2L by c, what happens? The negative pressure wave will come. This negative pressure wave will first diminish this delta H to H0, and at the same instant another negative pressure wave will start, as we have discussed earlier, in this direction. So the pressure wave at that instant t is equal to 2L by c will fall to a negative minus delta H. You see that? If you see this one, at 2L by c, this is the situation. Just at 2L by c, this wave will come, so here the negative pressure wave will fall. So therefore this is 2L by c, and we see again this will continue for a period of 2L by c, because the negative pressure wave will go here again and again will come back as a positive pressure wave, so that it will come, it will take time L by c plus L by c, 2L by c, so that again it comes to this situation. So this cycle of events will go on repeating like this with time. So this is the typical pressure fluctuation, a step type fluctuation with time at a point on the valve end. So what will be that at a point on the reservoir, at any point at a distance x from the reservoir end? What is that? At a point x from the reservoir end, if we consider, this is most interesting. You see, this is most interesting, that if this be the H0, well, so after the at time t is equal to 0, the head is H0, because it will take some time to reach here. It will take some time to reach here. So what is the time taking that wave, pressure wave to reach here? It is L minus C by, L minus x by c. L is this length of the tube, this distance is x, so therefore L minus. So after a time L minus x by c, the pressure head will go on increasing to delta H. So this is L minus x by c. So pressure head will increase to delta H. Now this will rest up to a time. So this pressure head will remain delta H, above H0 will remain so long this pressure wave goes here and comes back as a reflected pressure wave, which will take a time x and x, 2x by c. So during a period of 2x by c, this pressure wave will be delta H. So after that, what will happen? The pressure wave will superimpose a negative pressure wave and it will fall at 0. So it will remain 0 so long this pressure wave goes here, You understand? And again another negative pressure wave comes here, which will take a time of 2 into L minus, this is L minus x by c. So for a period of 2 into L minus x by c, that means this period. So let us write this 2 into L minus x by c up to this period. So it will be at a head h0, after which it will be again at a negative head. That means this negative pressure wave will reach here. So this will be again this negative head. This will be creating a negative head when the pressure wave, negative pressure wave will pass through this, and it will remain to that head delta H to up to a time period that this negative pressure wave goes here and comes back again from here as a positive pressure wave. That time is again 2x by c. So again it comes to the positive pressure. So this pressure wave, when it passes through here, it makes the pressure at H0. And it will take a time L minus x by c when this pressure wave reaches here. So this time also we see, so this is L minus x by c. So this point will correspond to this point. From here again after L minus x by c, this cycle will start. That means this point corresponds to this point. So if we add up all this time, L minus x by c, 2x by c this, so the time period of the cycle is 4L by c. But the pressure fluctuation is like that, from t is equal to 0 up to a time L minus x by c, where c is the wave velocity, pressure wave velocity relative to the liquid, there will be H0 head, initial head, at any point x from the reservoir end. Then immediately the pressure will increase to delta H, and it will remain to a value of H0 plus delta H over a time interval of 2x by c, where x is the distance from the reservoir end. Then the pressure will again fall after a time of L minus x by c plus 2x by c, this time interval, and it will remain at H0 for a time interval of 2L minus x by c, which is the time taken for the pressure wave to go to the valve end and again coming back to this point. Again the pressure will decrease, that means the pressure rate will be H0 minus delta H for a time interval of 2x by c. And at this instant, given by this time from initial time, this will be again coming to the initial H0, initial pressure rate, and this is the point corresponding to this point when the pressure wave has reached, that is the positive pressure wave has again reached to this valve end. So this is the typical pressure fluctuation at any point x in the pipeline due to this repeated movement of the pressure waves. Now we will come to the concepts of rapid and slow closure. We will come to the concepts of rapid and slow closure. What is meant by rapid? Let us consider again a pipeline with the valve under some head of liquid. So this is suddenly closed. What is meant by rapid and slow closure? Now in practice, no valve can be closed instantaneously. So far we have considered the valve is closed instantaneously. That means at t is equal to 0, we start telling that the decompression of the fluid adjacent to the valve has taken place. That means the pressure wave has start moving from the valve end just at t is equal to 0, which means we consider at t is equal to 0, the valve is completely closed. But the complete closure at t is equal to 0 is impossible. There is always some finite time taken for the valve to close. Now if this time is taken as Tc, then we see that one very interesting thing, that so long Tc is less than 2L by C, the pressure head generated at the valve end will not be changed from the previous quantity. That means we know that pressure head generated due to the total deceleration of the fluid is Cv0 by G. Now if the valve is not closed immediately, this is the instantaneous closure, valve is closed during a time of Tc. So what happens? During some time less than Tc, so valve will be partially closed where the velocity of the fluid is decelerated from V0 to some other velocity V1, for example, V0 to V1. So the pressure rate developed will be less than this. In that case, the pressure rate developed in that case delta H1 is Cv0 minus V1 by G. So what happens? The pressure rate will gradually develop to Cv0 by G when the valve will be fully closed. Now if this closure of the valve takes a time less than 2L by C, then what happens? Before a negative pressure wave, a reflected negative pressure wave comes here. For example, the pressure wave which was generated at the beginning, the first pressure wave, due to the first closure of the valve, with the very fast pressure wave which is generated for the decelerating of the liquid, we will take time 2L by C to travel to the reservoir end and come back. So before any reflected wave comes, to the valve end, the entire pressure will be developed, because the valve will be completely closed, and so that entire pressure will be developed. That means sigma of all this delta H1 will be delta H. So before any reflected wave comes to the valve end, the pressure development is the same as that for an instantaneous valve closure. So this case is known as the rapid closure. So when Tc is less than 2L by C, we call this as a rapid closure, which gives the same pressure rate developed at the valve end as that in case of instantaneous closure, and the physical situation is same. Now we consider the case when Tc is greater than 2L by C. What happens? That means before the valve is completely closed and fluid is completely brought to rest, a reflected wave will arrive here, because the first pressure wave we generated will go to the reservoir end and come to this valve end by a time of 2L by C from the beginning, T is equal to 0. So if the time of closure is more than 2L by C, so before the valve is completely closed, a reflected pressure wave will reach here, so that it will not allow the liquid to attain its maximum head or rise in head as it could have obtained by decelerating the fluid instantaneously. So this is known as slow closure. And if the closure is still very slow, that means much more than 2L by C, in that case the compressibility effect may be ignored. That means this does not come into the consideration of a rapid change in the flow velocity, so that compressibility comes into consideration. So therefore we can write that there are three types of closure. When equal to 0, this is instantaneous closure. When Tc is less than 2L by C, this is known as rapid closure, where the pressure rate developed will be the same as C V0 by G as that of the instantaneous closure for the valve end, and Tc I am greater than 2L by C, Tc less than equal to 2L by C, rapid closure. Greater than 2L by C is slow closure, where the pressure rate developed even at the valve end will be less than that developed for instantaneous closure or rapid closure. Or Tc very greater than, very slow closure, very slow closure, where the compressibility effect, compressibility effects can be ignored. Now most interesting fact is that even if there is a rapid closure, Tc is less than 2L by C, in a pipe, the entire pipe does not reach the maximum pressure rate generated. Only the valve end always reaches the maximum pressure rate generated. This is obvious. This is because if the valve closure time Tc is there, which is less than of course 2L by C, then though the valve end the pressure rate developed is C V0 by G, but this is not true for any other point. This is because the time taken for any other point to receive a negative pressure wave after the time when a positive pressure wave has changed its head will be less than the point to suffer the maximum change in head. Well, so let us find out that up to what length the tube will be suffering the pipe will be suffering the maximum change in head. Delta H is C V0 by G. How to find out it? Let this from the reservoir end, this point distance x. That means we specify the problem that L minus x is the length from the valve end. That means this is L. From the valve end, the L is the length. So L minus x is the length which will be subjected to the maximum rise in pressure. How to find this value, the maximum rise in pressure? This can be found out by the value by equating the time which is taken by the wave, reflected wave, to move from this position going to the reservoir coming back with the time required for the pressure to be generated here. Now you see the first wave will reach here at a time L minus x by c, first pressure wave. Then if Tc is the time of closure, so we can tell from time t is equal to 0, this is the time taken for this part of the pipe to be raised to this maximum pressure rise, because L minus x by c is the time taken for the first wave to reach here, which will increase the pressure rate to some extent. Then Tc is the complete closure time. So after that, if we add L minus x by c, Tc plus this, so after this time the entire pipe will be at the maximum pressure rate rise. If this is equal to the reflected wave for the first pressure wave to come here, that means first pressure wave was generated here at t is equal to 0. So it has reached here at a time L by c from t is equal to 0. The first pressure wave reaches here at L by c time, then comes here plus x by c. So therefore, any reflected wave to appear at this point for the first time, this point has already changed or suffered the maximum rise in the pressure rate. So if you make an equation like that, we get L by c cancels, we finally get x is equal to Ctc by 2. So L by c cancel, 2x by c is equal to Tc, so x is equal to Ctc by 2. So depending upon the value of Tc, x will depend. That means if Tc is equal to 0, that is instantaneous closure, x is equal to 0. That means the entire pipe will be subjected to the maximum pressure. Now you see Tc is equal to 2L by c. You write Tc is equal to 2L by c. What is the x? 2L by c, that is L. That means it will be only at the valve end. That means at the extreme time, that means Tc is less than equal to 2L by c for a rapid closure. That means when Tc is equal to 2L by c, then the maximum pressure rise will take only at the valve end. But Tc is less than 2L by c, if you see x will be, so x is not, x will be less than L. If we put Tc less than 2L by c, we get x is equal to L. That means x is less than equal to L depending upon Tc less than equal to 2L by c. So Tc is greater than 2L by c. So we see that x, that means none of this, that means x will be greater than L. That means the none of these pipe, that means not even in the valve end, the pressure, maximum pressure rise will be occurring. So this is the concept of rapid closure and slow closure. Okay, now I will come that to a thing that how we can find out for a slow closure the change in the pressure head at the valve end, how we can find out. The problem is like that, if we consider for a slow closure, the velocity is changing from V0 to V, for example V0 to V1. Then we can write the delta H, that is the pressure head rise for this slow closure, is delta H1 for the first step. Now before that we consider, we must tell, I have forgotten to tell you that this slow closure problem, that means Tc, slow or rapid closure problem, that Tc either less than equal to 2L by c, or rather I write here Tc, that means Tc, any value of Tc greater than 0, which is either rapid closure or slow closure. The problem is thought in this way that the valve closing is considered in discrete steps. The valve closing is considered in discrete steps, which is continuous in practical situation, considered to be in discrete steps of time, which are multiples or sum multiples of 2L by c. And we consider that the valve, entire valve closing, which is actually a continuous operation in practice, to be in steps of interval of 2L by c or sub interval of 2L by c, and in each discrete steps it sends a pressure wave which raises the pressure of the fluid and decreases its velocity, and during that time the valve remains stationary, after which, after the entire fluid is being pressurized and decelerated, then another step of valve closing takes place. Okay. So with this idea, if we consider the first step of valve closing, that first step of valve closure, so liquid velocity is changed from V0 to V1. So delta H1 is C V0 minus V1 by G, not C V0 minus 0 by G. This will also can be found out by writing the momentum equations. This you can find out by writing the momentum equations through the pipe, so that we can get delta H1 is equal to C V0 minus V1 by G. Now, if the initial head is H0 and final head is H1, then we can write H1 and delta H1 as H1 minus H0 as C V0 minus V1 by G. This is the pressure head rise because of the deceleration from V0 to V1. Now, here there are two unknowns, H1 and V1, to be found out. We do not know up to what velocity the liquid has been decelerated. So, to do this, we require to find these H1 and V1 simultaneously, we require another equation. To get another equations, we consider the valve opening like this, that this is the valve opening through which the fluid is being discharged with a velocity of V1, but the fluid is approaching this with a velocity V1. So, this is the V1 with a velocity V1 as an orifice. That means the partial closure of the valve will act as an orifice. How? When orifice, we know Q with an orifice whose Q is given by CD, the coefficient of discharge is working like an orifice. What is the orifice equation for the rate of discharge? CD into area of the orifice into root over 2GH. So, here Q can be written as area of the pipe A into V1, that is same which is coming from here. Even if the area opening of the thing is different, that is CD into area of the orifice, that is the area of the valve. That is the valve opening after the first step, that valve is partially closed, and root over 2GH1. So, we can write V1 is CD AV by A into H1 to the power half. So, this is a constant usually, though the coefficient of discharge for this valve opening varies with the velocity, but we can take this as B as a constant and known as valve opening factor. So, therefore, we see valve opening factor. Therefore, we see we have two equations. If we know the value of the valve opening factor V1, B, so we get V1 is some constant B, which is the valve opening factor, comprises this CDAVA root over 2G times root over H, and another is this. So, simultaneous solutions of these two equations give the value of H1 V1. That means we can find out what is the pressure rise in the first stage and the corresponding decelerated velocity after the first step. This way each steps are calculated in this process. Well, now at the end I will tell you the most important thing in practice because of this water hammer problem, what is the implication of surge tank. Now, in a hydroelectric power stations, as we know, when the liquid is fed from a high head via a penstock to a turbine, then what happens when the turbine load changes, the flow of water has to be altered. So, this causes sudden acceleration and deceleration in the long penstock leading to the turbine, and which faces severe water hammer problem. For example, when load is increased, so water flow has to be increased. When the load is decreased, sudden deceleration of the water has to take place, for which the pipeline, that is the penstock, suffers the water hammer problem. To reduce that problem, a surge tank is used. That is nothing but an open tank which is placed very close to the turbine attached to the penstock, so that a long portion of the penstock, that is the pipe leading to the turbine from the large overhead reservoir, suffers. A large portion of that does not suffer the water hammer problem, whereas a small portion from the surge tank to the turbine suffers the water hammer problem. Let us very quickly see this thing. Let us consider this is this. Now, you see that this is the pipeline. So, this is the tank. Well, this is the tank, and this is the turbine. Look, this is the turbine, this is the valve, this is the valve V. So, this is the reservoir R from where the water is coming to the penstock. So this part of the penstock is laid at a lesser slope, and this is the surge tank whose height, this top is higher than this. So this is the water. So what happens when the load is reduced? So this valve is suddenly closed. So surplus water goes to the surge tank, so that the head in the surge tank goes on increasing, which gives a decrease in the head, causing flow between reservoir and surge tank. So the water flow in this long part of this penstock, this pipeline A to B, is gradually decreased and doesn't face the water hammer problem. Whereas B to C, only the lesser part of this penstock suffers the water hammer problem, for which the surge tank is placed very near to the turbine. And another thing, when the flow is increased, when the load is increased, suddenly the flow is increased, what happens? The surplus flow comes from this surge tank to this pipe, so that this pipe does not face a sudden acceleration of the flow. So therefore, by providing this surge tank, we can avoid the water hammer problem. When the deceleration is very sudden, so that more water has to go to the surge tank, the surplus water here, to reduce this flow in this pipe gradually, the overflow line is there, so that water can overflow from the surge tank. So therefore, from this application of the surge tank, we can tell that surge tank S reduces the water hammer problem in the greater part of the penstock when the flow is reduced due to the reduction in the load, and at the same time it meets up the surplus water when the load is increased, and also it takes the surplus water when the load is decreased. This is the principle of a surge tank. Surge tank is usually cylindrical here, but in many design a surge tank with varying cross-sectional area with the height is provided instead of a cylindrical one, because of its flexibility in operation and because of its fastness in operation. So therefore, again and again I am telling you, the providing a surge tank, this is a very practical aspect. We see that the water hammer problem, that is the sudden acceleration and deceleration for a long part of this pipe, is reduced, and at the same time surge tank acts as a reservoir type of thing, which gives the extra water or takes up the extra water when the load is altered. Okay, so that's all.